to say is it true or false. The slip system in a BCC crystal is 111, this is your plane, and 110 is your direction. So is it true that this is your slip system in a BCC crystal or not? So what do you feel? What is the right answer?
Ma'am, false it is.
It is false. So why is it false? So what is the right answer for the slip system in a BCC?
Ma'am, it should be reverse. It is 110 and
Right.
the
So we
direction is
have
111.
110. 110 is our plane. That is a slip system, and 111 is our plane direction for a BCC crystal. So it is reversed, right? So the answer is false. Okay. So next question says efficient slip system should have loosely packed planes with a higher interplanar spacing, densely packed planes with a higher interplanar spacing, densely packed planes with a lower interplanar spacing, loosely packed planes with a lower interplanar spacing. So you know that if you have a slip system, the slip system is defined by a set of plane and a direction. So you have to say is which of the plane, which a slip plane is nothing but it is a plane through which there is a likelihood of deformation, plastic deformation to occur in a material. So it will be on a certain plane in a certain direction, right? So you have to say what makes a plane or say for example slip system qualifying to it to be called as a slip system. Is it loosely packed planes or densely packed planes? First we'll talk about the packing of the planes.
Ma'am, loosely packed planes.
Okay. No. For a slip system to occur, for any slip to occur, you should have a densely packed plane. That is why we said when you have a HCC crystal, if you have seen a lecture, you should have the atomic arrangement densely packed. All the atoms should be, all the voids should have been occupied, and you should have a dense packing. Then only the system will slip will occur. Slip always occurs on a plane which is densely packed first. So this is either of the two are right. So then we have to see what is the interplanar spacing. So the interplanar, with respect to interplanar spacing, we should have a higher interplanar spacing for a efficient slip system. So the option B is right, that the atomic arrangement should be closely packed. Second, the interplanar spacing, which is just nothing but the distance between the two planes, right? That should be high interplanar spacing. That will qualify it to be a efficient slip system, right? That is why it will slip from one plane to another. So for you should remember, for efficient system you should have a densely packed plane and you should have a higher interplanar spacing. So we have next question that says mechanical twinning is usually seen in materials with HCP structure, materials with FCC structure, with VCC structure, and it is not dependent on crystal structure. So you have to try to answer. So what do you feel is the right answer? You know that
HCP.
yeah, right. It is actually the HCP structure. If you understand, if you have a very, for example, if you have a structure which is very highly densely packed, which is close packed structure, which is having proper slip system, that is FCC with 12 of its 12 planes, 12 slip systems possible for a FCC structure. So that in that case, there is a more probability of occurring of slip rather than the twinning. But twinning occurs in those structures where you have a very weak slip system. You do not have a very efficient slip system to occur because there is no good plane for any mechanical deformation to slip, right? So you have to see for that. So you know that FCC has a very good closed back structure, so it is not it is a very efficient system with having a slip system. So FCC is not a right option. BCC also does not have a very clear defined closed back system, like all the planes are not closed backed, but it is much better than HCP structure. So HCP structure is the one which is having very inefficient type of slip system, and that is why more it is more prone to uh, like mechanical twinning. Okay. Okay, so we have another question. What is the total number of possible slip systems in an FCC?
One 12.
Yeah, this is right. So we have 12 number of possible slip systems in FCC. Now the next question says, if sigma denotes the true stress in the material and S denotes the engineering stress. So we have two true stress and we have engineering stress. Then the relationship between the two is. So you have to say what will be the relationship between your true stress and between your S, which is like engineering stress, out of the following options.
And the first one is the correct one.
First is yes. So right, I think first one is the right one. So this is how we are trying. You know how we can try to like arrive at this. You don't have to remember, but you can do it in a like simple calculation. You know your true stress for a material is actually given by your force per unit area, right? First, how much area it is occupying, right? On the area on which the load is applied. While as your engineering stress, this is actually the area, instantaneous area, right? So we can write it as A. So then we have S, which is actually your engineering stress, that is actually the force per unit area, actual area, that is initial area that you had taken for the deformation. So you just have to solve these equations. So you can write the sigma equal to P by A, and you can multiply it both sides by, say for example, A naught. Then you can try to solve it for a yes, because you know that the volume is conserved. So the conservation of volume says that your area and your length will be conserved. So A naught L naught is equal to your A1 or A1 L1, right? I can write it like this. Say, so then you can replace this A naught by A in this equation, and you can write P multiplied by L1 by L naught, P by A naught first. So then we will have L1 by L naught, right? So you have some kind of a this relationship, and then yes, you know L1 by L naught is nothing but it is E plus 1. So you can write this P by A naught is your this S. So you can write finally the equation will arrive at sigma is equal to your true stress multiplied by 1 plus E. Okay, this is your final equation. Just have to solve the two equations and arrive at the final equation. Okay, you have increased its strength. Now you want to reduce some of the work hardening and you want to optimize the parameters. So which of the following process you should use? Is it recovery, cold working, recrystallization, or impact loading? You have to relieve some of the work hardened stresses in the material. So how can we achieve that? You know, you understand that after work hardening you have done some work hardening in the material, and now your structure is having certain strength in the material. Your grains look like these. So most often after your, this is nothing, cold working is nothing but it is simply you are work hardening the material, you are deforming it, and you are creating a number of dislocations in the structure to increase its strength. So this is a strengthening mechanism. This is something that cannot reduce the strength, but it will increase the strength, right? And also we have now recovery and recrystallization. These are two types of phenomenon which are done post cold working treatment or post work hardening in order to reduce the stresses. So right answer is recovery and recrystallization. These are two different processes. First occurs the recovery, that is when you are at a lower temp, you try to take this material which you have deformed or you have work hardened, you subject it to a certain temperature in order to relieve some of the stresses present in them. And by subjecting it to certain temperature in initial stages, the recovery of the grains happens. That is, they try to relieve the extra stresses that is accumulated in the grains, and then you the second stage occurs in which recrystallization occurs. So you have a growth of your grains, like stress-free grains. They are not stressed grains. So you have relieved grains. So recrystallization, that means again the crystallization takes place. So that is another process for that happens for this that is done post cold working treatment. So recovery and recrystallization help in reducing your strength of the material, while if you are going for a cold working, it will increase your strength of the material because number of dislocations will increase, and that will help in your plastic deformation of the material. Okay, so we have another question that says if sigma 1, sigma 2 and sigma 3 are the three principal stresses acting in the material, and the order of their stresses is given as sigma 1 greater than 2 greater than 3, then the maximum shear stress acting in the material as per Tresca criterion is given as, so you have to say which one is the right option. This is very easy question.
Second option.
Second option, right, because we have to see the highest and lowest stresses that are acting on the material. So we have this as a lowest stress, and then we have, sorry, highest stress, and this is as a lowest stress. So the subtraction of your highest and lowest stress divided by 2, so you have to take the average of that, will help in you determining the maximum shear stress acting in the material. So option 2 is the right option. So you have to bear in mind what is the order of their stresses, and then accordingly decide your maximum shear stress. So now we have another question that says, although a body-centered cubic material has 48 slit systems, still it exhibits lower ductility than a FCC material, right? So you have to say this is your question, and the reason for this is given that BCC has a closed pack planes and directions, whereas FCC does not have. So you have to say which of the following is right option.
Ma'am, first one.
Right. So it is saying that the assertion is right. That means this statement, which is the first statement, is right. That you have a body-centered cubic material which has large number of slips, but it is having a lower ductility than the face-centered cubic material, right? So that is because that is right, but the reason is given that BCC has a closed pack planes in directions, whereas FCC does not have. While reverse is true, that FCC has closed packed planes, while BCC does not have the closed pack planes. So that is why we have FCC, because of the closed pack structure. We are having much more like ductility in FCC structure than in BCC structures. So the option A is right. The reason is reverse of it. The right reason is that FCC is having a closed packing while BCC does not have. So we have another question that says the tensile stress is applied along 110 or axis of a silver single crystal. Okay, so you have a single crystal. You know that for a single crystal you only have you don't have much deformations to take place. It has only one dislocation. So you have a single crystal of silver and you are applying a load along 110 axis, right? So we'll try to draw this diagram. So it is saying that you are applying the load along 110 direction. So this is your 110 direction. And it says if slip is started on the 111-101 system, then what will be the yield stress of the material and the critical resolve stress is given. So you know you have some plane inside this crystal that is subjecting to this tensile load, and you have a slip starting on a certain system which is having direction and it's with plane and the direction. So this plane which we are choosing, it is actually 111 plane, right? So you know if the plane is contained in this is your plane and it is having a 111, it is called as 111. So the normal of this will be 111 also, right? So this is 111 direction, while as your slip direction is 101, sorry. So this is your slip direction. So this is your, we can say 101, right? So you have three directions. One is normal to the plane, that is because the plane was 111, its normal will be 111. While we have a slip direction which is 101, and we have a tensile along which the load is being applied. So then what will be the yield stress? So this is some strength, that is something we have to calculate, and your critical resolve shear stress is given. So you know the relationship between your critical resolve shear stress, right? That is nothing but that is dependent on your yield strength and angle, that is cos of your two angles. The angle, one angle is this, the one between your tensile axis and the normal axis. So this is one of your angles, so we call it phi. And you have another angle which is called as lambda, which is the angle between your tensile and your slip direction. So you have cos of phi and cos of lambda, right? You have two directions. Now you have to calculate the sigma y. So we will rearrange it. We will write tau r, which is a critical resolved shear stress, divided by these cos values, cos of phi, okay, and cos of lambda, right? So that will give you your yield stress. Now what we have to do, we know this TRSS, that is 7 ampere, that is given in the question. We have to calculate cos of phi and cos of lambda. You know, whenever you are talking about crystal structures or crystal geometries, whenever you have to find an angle between the two directions, it is given by the cos of angles, it is given by a certain formula. Always any directions you are given in a system, any two directions, and you want to find their angle, you can use the simple formula. Say for example, first we'll find cos of phi, so that will be equal to, it is simply equal to, for example, I'll write it in the first formula form. So this will be h1 h2 plus k1 k2 plus l1 l2, right? And divided by your square root of planes, right? Miller indices, h plus s square plus k square plus l square, and you are given for other system also similarly, right? So we will try to solve it. We will try to now see what is cos of phi. Okay. So we have first the dot product, that is 1 cross 1, that is plus this 1 into this 1 multiplied. So 1 plus this 1 multiplied by 0. So that will be 0 divided by the square of this. So this will be under root of 3 multiplied by under root of 2. So that will be 2 divided by root 3 multiplied by root 2, or we can write root 6. Okay, so this is your for cos of phi, and then you can find for cos of lambda also, that will be 1 multiplied by this 1, so this is 1 plus 0 multiplied by 1, that is 0 plus 0. Okay, and you have square root of 2, and you have square root of this, so this is again square root of 2, so you will have 1 by 2, right? So now you can put the values in this equation. Simply you have 7, your critical resolve shear stress, the cos of your phi is now, you know, that is 2 by 2 under root 6, and then you have multiplied by cos of lambda, that is 1 by 2. So now you can tell me what is the right option.
17.1.
17.1, that is last option. Okay, so this is your correct answer. So you can calculate your yield strength based on your angles between the planes and based on your critical resolve shear stress. Okay.
Ma'am, would you please how did you draw these directions on the crystals? The single silver crystal is given.
Yes.
How did we determine the direction like 110 and 111?
This will be given, but because it is a single crystal, you should know, for example, if you have a silver, what is the crystal structure of silver? First, you should know that. If you want to find it yourself, right? So, if you know crystal structure of silver, silver is, for example, it is a FCC structure, right? So, FCC structure, what is the closed pack direction? The closed pack direction and closed pack plane. So, this is your closed pack plane, 111, and this is your direction, right? So it has chosen one direction and one plane from your FCC structure, which is a closed pack direction through which there is a possibility of slip to occur. So that will be your slip direction, but most of the time it will be given in the question because you won't be remembering the crystal structure. So that way you can also calculate. If you know it is a silver crystal, you can take its slip plane and slip direction and then calculate it.
Ma'am, how did you find the direction of tensile axis?
This is given. This is a tensile stresses applied along 110 axis.
Nee, my question is that how did you match with the vertical axis only?
Like this is your plane. You make a plane which is because this is a critical resolve shear stress. You know it is at certain angle to your tensile stress, right? So you make this plane. Now given in the question is that you have 110 as your direction. So I make this 110. Then I have to see what is the slip direction. It is given 101 is the slip direction. So I chose this as my slip direction. And then I had to see what is the normal of this plane. So that will be 111. So I choose the normal of that plane because the plane is given, it is 111. The normal to the plane will be one, the direction which will be normal to the plane will be the same, that is 111 only. So I choose this direction. So now I can calculate.
Okay, ma'am. Got it.
So then we have another question that says strain hardening will be highest in HCP materials at high temperature, HCP materials at low temperature, cubic materials at low temperature, cubic materials at high temperatures. So all of this is just nothing. You just have to remember all of these questions are related to your plastic deformations, to your number of slip systems, to your ease of slipping in a system. So all of this are interrelated, and that is how these questions are framed, right? So you have to say how will the strain hardening be highest. So you have two parameters here. One is your crystal structure and one is your temperature. So you are saying that there is some relationship between your strain hardening, which is cold working or work hardening, with respect to your crystal structure and your temperature. So now you have to say which is the right option. See, if you first compare the crystal structure, so you have two crystal structure here, HCP and cubic material. Out of HCP and cubic material, which will have a tendency to strain harden more, HCP or cubic material? Simply because of based on your number of slip systems, right? Number of your closed pack directions. So which is more prone to undergo strain hardening out of the two systems? First, we'll talk about systems, which are crystal structures. This is one part of the question, and the other part is your temperature, right? So first tell me which is the right option for strain hardening will be highest in which CP or cubic material?
Ma'am, I think cubic materials have more slip systems.
Yes, cubic systems have, yes, not only more slip system but also closed pack systems, right? The closed packing of the material is more responsive, right? So cubic system will have either this option or this option, right? Both of them have a higher strain hardening. Now we are talking about temperatures. What happens at higher temperatures, that your dislocations tend to annihilate, or they are reduced. Your this number of dislocations are like only high temperature treatment is done, like annealing is done to relieve your stresses in the material caused due to strain hardening, right? So at higher temperatures, your structure undergoes recovery and recrystallization, and you're trying to reduce your dislocations, and somewhat your strength of the material or strain hardening is reduced at higher temperatures. But at lower temperatures, there is no such effect. You have the like deformations or dislocations present in the material as such. So this option is right, that you have to see a cubic material, and that should be at low temperature, that will have a higher strain hardening. So you understand from this point that you have both structure, crystal structure, and your temperature affecting your strain hardening behavior in the material, right? So you should understand what is based on your crystal structure, how many slip systems are there, which are closed back uh, uh, directions planes. So that will influence your strain hardening mechanism, and how by with respect to temperature your recovery recrystallization will be influenced, and how it will relieve the hardening in the material. Okay. So we have another question that says, if the true strain.
Ma'am, excuse me.
Yes, yes.
Madam, had there been a third option in terms of crystal structure, say HCP? Ma'am, what would be the correct answer? HCP at lower temperature?
Yes, also for HCP, the temperature will have the same effect because.
If there is a third option,
Mm-hmm,
that means, see, there are two structures given, HCP and cubic.
mm-hmm.
Had there been the third option, say FCC?
But we are including the FCC in the cubic material only. FCC is nothing but it is a face-centered cubic,
Okay.
right?
Cubic means BCC.
Cubic means both FCC, BCC,
Okay,
because it
thank
is
you.
face-centered cubic, body-centered cubic.
But ma'am, if we compare BCC with the FCC, ma'am,
Yes,
so where would we see more strain hardening at the
obviously in
same
FCC
temperature?
structure because of the efficient closed packing system.
Okay.
Yes. Okay. So we have another question that says, if the true strain curve after yield point is given by sigma is equal to 150 e raised to power 0.33, then flow stress of the material at a strain of this will be, so you have to calculate the flow strain, but you should understand that this is a true stress strain curve after the yield point, and it is given by certain equation, right? So you just have to calculate what will be the flow stress. Flow stress is nothing but it is your this stress, which is sigma, and you are given a strain of 0.7. You have to do nothing but you have to put the value of strain in the equation and calculate your stress. So you can try to calculate it.
First option.
First, also you should know that you have a normal up to elastic deformation. The stress strain curve is same whether it is engineering or true. Okay, but after that there is a change shift in the equation, right? This if this is your engineering stress curve, your true stress will be something like that. It will move upwards and it will move slightly leftwards, right? So there is some change in your stress strain curve when you are using, for example, for a true stress. So I can write here, this is your true and this is your engineering, right? So you should understand that up to sorry elastic deformation, there is no change in the equation, but it is only after elastic, which is after yielding. That is why we said after yield point it is given by this equation. So the equation for this portion, right, this portion is given by this value, right? So you are given y is equal to mx, this is just a equation between your y and your strain. So you have two equations and you are given the parameters for that. It is dependent on some strain, some raised to power 0.33, right? So it is dependency on epsilon is not a straight line, which is as is in this case elastic region. It is some other form because you have this equation, which is raised to power 0.333. Okay. So now you just have to plug in the value for the strain and calculate what will be the value of your stress.
First option 133.34.
Okay, so the first option is your answer, that is 133.34 MPa. Okay. So we'll move to next question. This is your next question. This says that a steel wire is attached to mass 7,000 kg. If we have to design a wire, so you have a wire, some steel wire here. So we have some wire here. This is your steel wire. So it is saying it is attached to a mass of 7,000 kg. So it is having some mass here, right? This is your mass, that is 7,000 kg. And if we have to design a wire, then what will be the minimum diameter which can lift this load without any permanent deformation? That means without any plastic deformation. Permanent deformation is nothing but your plastic deformation, right? Then it is saying what should be the diameter of this wire, right? Okay. So now we are saying that the UTM of the wire material is 700 MPa. So you are given an ultimate tensile stress of the material, and you are also given a yield strength, that is 2/3 of UTM. So you have to calculate the diameter of your wire. So you can take 5 minutes and try to solve it. Then you have to think how to approach this problem, and then we will try to solve it. You have to find the diameter of the wire. So you can try.
Ma'am, I have got the third option as the answer.
13.68. Okay. Okay, so how will we try to approach this question? First, we know that UTM of the wire is 700 and your yield strength is 2/3 of that. So if you go for yield strength, you know that is equal to 2/3 of your ultimate tensile, which is nothing but 700, right? So this is your yield strength. But you know that for any material, yield strength is given by your uh, equation, that is your force, we can say P, which is load here, and then your area of the material, that is the area on which the load is acting, right? So we have to say what should be the minimum diameter which can lift this load. So we know the load value, we know the value of the load, that is 7,000, because we have to calculate it in weight. So that will be 7,000 multiplied by the gravitational constant. So we can take it as 9.8 or 10. So area will be given by pi by 4, right? And your d square. So d square is something we have to calculate. This d is to be calculated. So you can simplify the equation. So you can calculate d square based on your values. So this will be, I'll just write it as such. So you can solve it later. This is 7,000 multiplied by 9.8 divided by pi by 4. Okay, multiplied by your yield strength, that was 2/3, multiplied by 700, right? So you can solve this. This is 10 and then you have 2 here. So you can solve it and you can achieve this answer, that is 13.68 mm. Okay. The next question says that in a highly ductile material, toughness dash with the strain hardening. Whether it increases, decreases, remains constant, first increases and then decreases with strain hardening. So you have to answer this. So you know if it is a ductile material, how will its curve look like? So you have to say how will the toughness and strain hardening be dependent on each other.
Increases.
Uh, See, it is increases is fine, but see, for example, if you have a sigma and this curve, which is a stress strain curve. So for a ductile material, your curve will look like something like this, right? Because it is a ductile material, it will undergo plastic deformation, but it will have a larger elongation. You can have more elongation in such materials as compared to any other material. So what happens? Toughness is nothing. What is toughness? Toughness is the area under this curve, right? So if you are increasing, first if you are seeing that the elongation is increasing because of your strain, like what happens when the material is very highly ductile, so the toughness will actually first increase with the strain hardening, but there comes a point when it actually decreases. Why? Because your toughness is a property of both. It is dependent on both your sigma and your epsilon. So it is a combination of your ultimate tensile strength and your this ductility or elongation, right? So because in first cases, in your initial times, your strain hardening, your ultimate tensile strength will play a role in increasing the toughness, but after a point when it will be strain hardened, after a certain duration of time, your ductility will come to play a role and your toughness will decrease. So your right option is that it first will increase because of your strain hardening, but because your ductility has a inverse role to play here, so then it will decrease, right? So the right option is D, because it is a
Ma'am, what will be happen if we choose a material which is normally ductile material, like low carbon steel?
right.
So, ma'am, in this case, what will be the correct answer? Because this is a special case when ductility is very high.
Yeah, but if you even have a normal ductile material, it depends. Like for example, what kind of interstitials are there? Because in a steel, which as you are saying, you can have some interstitial spacings in that. You can have effect of your grain size also comes to play a role. Your post heat treatment methods will come to play a role. So the system is becoming complex, so you cannot clearly say for such systems. But because this is a straightforward question for a ductile material, generalized question, so that is why you can answer. But for very specifically for a low carbon or medium carbon steel, you have to see the history of your steel, from where it is coming, what are the interstitial impurities, whether there is any other substitutional atoms, what kind of a heat treatment it has undergone. So all of these will influence your toughness and all parameters, right? So we have another question that says cohesive force of permanent magnets dash with increase in gold working, whether it increases, decreases, remains constant, first increases and then decreases. This question is actually to understand the direct application of your deformations. Like basically, what do you understand from deformations? You either understand that you are creating deformations, you are increasing the strength of the material, you are relieving the stresses, all of these properties, because you want to work on the material, right? You want to make it strength, you want to either increase the strength, or either you want to make it malleable or ductile for various drawing and applications for use, right? So these are normal applications that come to your mind, but also these cold working also helps in your indirect applications, whether there are some electrical properties, there are some magnetic properties in the material, they are also affected because of your plastic deformations. So In this question, you have to say what is the effect on your cohesive force when you are increasing the cold working. That is, you are strain hardening the material. So, what will happen to your cohesive force? Will it increase, decrease, remain constant, or first increase and then decreases?
Ma'am, would you please explain the meaning of this coercive force? What is mean by this one, ma'am?
Okay, so if you have a general idea of your magnets, for example, normally magnets have something like this. They are have hysteresis loop. We call it something like this, hysteresis loop. Sorry for the like this diagrams, but for hysteresis loop says that if you are increasing, this is your magnetization and this is your intensity of the magnetization. So, for example, if you are given a magnet which is, say, for example, because it is a permanent magnet, so you are trying to normally when you are trying to increase the magnetism of a material, you try to increase, you are increasing its magnetization, and your intensity of the magnetizing force also increases, right? And then if you go in this direction, you are magnetizing the material. If you are going in this direction, you are demagnetizing the material. So once you are magnetizing the material, you are increasing the magnetic field, you are increasing the intensity of the magnetic field, and the material achieves, because inside a material, what happens if you have a material, there are magnetic domains, something like these, right, which try to orient themselves in certain directions. If they are all in certain directions, they will have highly magnet, they will be affected by the magnetic field. But if, for example, there are magnetic domains that are opposite to one another, they try to cancel each other. So that is based on the arrangement of the magnetic domains. You will have different types of say for example, magnetic materials. Now what is cohesive force? Cohesive force is like when actually you try to magnetize a material, it reaches a certain highest magnetizing point, so it is magnetized. Now you remove the magnetic field and it gets demagnetized. But when it goes demagnetized, it never reaches the zero position. That is the curve that it has followed. It will not come back through that, but it will come through another region, and it will have some residual magnetism in it, right? Because you have certain this is your residual magnetism in the material, so it will not be completely demagnetized. So it will have certain magnetism, which is residual magnetism on demagnetization. So in order to remove this residual magnetization, you have to apply some external force, which is known as a cohesive force, to demagnetize, to remove this extra demagnetization. This is because you have to work against the magnetic domains of the material that have not completely reoriented to their initial position, right? So they had some X kind of a arrangement in positions is starting after magnetization. They have arranged themselves in some y directions, but when you are demagnetized, they are not completely returning to their X position, but they have some, say for example, another kind of arrangement, which is Z type of arrangement. So in order to come back to your X type of arrangement, you have to demagnetize, you have to apply some external force to remove the residual magnetism in the material. So you have to see how will it be related to your cold working. So first you have to see what will happen in cold working. When you are going for cold working, you are actually increasing the for example, you are increasing your number of defects, or you are increasing the number of your dislocations, or you are creating more hindrances inside the material, right? So because of the higher this magnetism in the higher cold working in the material, they will create a resistive forces inside the material, if it is for example a permanent magnet, and these resistances will hinder your cohesive force. So for example, if you are earlier applying, before cold working, if you are applying a cohesive force of, for example, F1 magnitude, but after cold working you are applying a cohesive force of F2, this F2 will be higher because you have to overcome the defects or the misalignments created in the structure because of your cold working. So your force after your cold working will always be higher than that was initially. So the cohesive force of permanent magnet will actually increase with increasing the cold working. So that is because there is more resistance in the structure now, and you have to apply some extra force to overcome that resistance apart from the normal force that you had to apply to remove the residual magnetism, right? So there are some effects of your cold working, on the properties of the material, not only on their direct properties. Like direct properties means your strength, your ductility, malleability, but it also depends on your indirect properties, which are their magnetism, their electrical conductivity. So you should have a relationship of these. You should understand the relationship between them also. Okay, is it clear?
Yes, ma'am.
Okay, so we'll move to next question. That says that the polycrystalline metal will work harden more rapidly than a single crystal. Is it true or is it false? So which is more difficult to work harden? Is it the single crystal or a polycrystalline material?
Madam, polycrystallines are difficult to get hardened.
No, but like we have a question that says the polycrystalline metal work harden more rapid. Then that means which is it that polycrystalline are easy to harden or single crystalline are easy to harden? Which of the two is which of the right statement is true? Is it true or false?
True.
Uh, right, true. Because why? Because when you have a polycrystalline material, polycrystalline means that you have many crystals in different directions, right? You have large number of crystals oriented in different directions, and as you have different orientations and different crystal directions, you have a number of dislocations happening more. Number of first, second, the number of dislocations, if they are more, there will be more pinning of the dislocations because of your grain boundaries. But for a single crystal, because it is a single crystal, so there is no hindrance, so this will not have as easy effect of dislocation hindering, dislocation pinning, or dislocation hindered motion. That is important for your work hardening material. So your polycrystalline will be always easy to work harden as compared to your single crystal, simply because there are more number of sites for dislocation hindrance, more resistance in the structure, and there will be more pinning happening, so that will help in hardening of the material more easily, more defects, more easy to harden, right? While in single crystal we don't have much defects and it's very difficult to make a hardening of the material possible. Okay, so the next question says which statement.
Excuse me, ma'am.
Yes.
Ma'am, what is the exact meaning of pinning? Because sir has frequently used this word pinning in their video lecture. Would you please explain what is meant by pinning of
Like
dislocation?
if I talk about the grain boundary pinning, what happens, there are number, for example, if you have this large structure and you have, say for example, I'm showing two crystals here. If I have, there is always some point of dislocation, like from where the dislocations originate. So there are, for example, dislocations originating in this grain and in this grain also, and I have the dislocations that are approaching this grain. I'm say talking about grain boundary pinning, say for example. So I have these dislocations that are approaching to this grain, and there are also dislocations approaching from this grain, right? So as they approach this grain, they are they are not easily, it is not easy for them to cross over, right? So they get accumulated near the grain boundary. So what happens, they are pinned to the grain boundary, and this creates further hindrance in the movement of the dislocations. As the movement of the dislocations is hindered, your material is strengthened, right? So grain boundary pinning, or or it also happens if you have a, for example, some precipitate forming, or you have some solid solution precipitates formed, so that also help in pinning. So pin is something that will hinder the easy movement of your dislocations, and as a result your material will be hardened. So pinning is nothing but it is a resistance to your movement of dislocations that occurs because of certain element, either because of the grain boundary or either because of some solid solution that is present in your, or precipitate present in the material, that will hinder the movement of dislocation, and as a result your strengthened material will be more, while your ductility will be decreased. Okay,
Thank you.
so we have another question that says which statement is false. So you have to say which of the following is false. So we have, with an increase in the degree of cold working, ultimate tensile stress increases, right? Ultimate tensile stress increases with a decrease in temperature. Okay. Ultimate tensile increases with an increase in grain size. So which of the following is true? So which of the following is true?
Ma'am, first one is true, ma'am.
Okay. Because with increase in cold warming, obviously you have more number of more stress in the material, so the ultimate tensile stress will increase. Second option.
I think this second option is false.
It says that the ultimate tensile stress increases with the decrease in temperature. This is true because if you will increase the temperature, your stresses will be undergo recovery and recrystallization, and your stress will decrease, right? So temperature always tries to annihilate the effect of your strain hardening. So this is also right. This is true statement. So I should not write trick. I should write true. This is also true. Then we have another question that says UTS ultimate tensile stress increases with an increase in grain size. So what happens if you have two grain sizes? For example, you have one coarser grain size. We discussed this, and then we have something which is a finer grain size. So what happens? Which will have a more tensile stress? This is the same based on this question, similar to that. More number of grains, more number of dislocations, more if you have more number of grains, you have more hindrance to the moment of dislocations, right? This is having easy moment of dislocations, but this will have a difficult moment of dislocations, and that will hinder your for example, if your dislocation moment is hindered, that will help you in increasing the yield stress of the material, right? That is what we are trying to do, strain hardening. We are imposing a restriction on the moment of dislocations. That is how we are strengthening the material. So if you are having a finer grain size, your ultimate tensile stress will be more in your fine grain size, while your ultimate tensile stress will be less in your coarse grain size. So it increases with an increase in grain size is wrong because it decreases with your increase in grain size. Okay. Now we have
Ma- Ma'am, for the option B, in many of the books it has been written that a material behaves like a brittle material at low temperature.
yeah,
Even
that is
even its
because if
bulk property is like ductile, but at very low temperature in the cold condition, it fails very easily because of the
because
brittleness induced due to temperature fall, ma'am.
right,
So
right.
is it contradictory to what you have said for the
No,
option B,
no,
ma'am?
no. That is right because we have a certain temperature where the material undergoes brittle to ductile transformation. Like sorry, ductile to brittle transformation. But those temperatures are very low temperatures. I am just saying it increases with the decreases. So these are normal room temperature temperatures and some above. We are talking about ambient temperatures. We are not talking about very low temperatures at which the transformations take place, right? So we are also talking about ultimate tensile stress. So that will
Thank you.
be dependent on your temperature. This one that with increase in temperature, your recovery and recrystallization will occur, and your ultimate tensile stress will decrease. Right?
Yes, ma'am.
Okay. Then we have another question that says which material shows the yield point phenomena? Copper, aluminium, steel, or silver? First, what is a yield point phenomena? Yield point phenomena is that there is a certain, you might have seen for certain materials that you have a curve like this and there is a decrease in the yield point and then you have something like this. So this is called as yield point phenomenon where there is a certain decrease in your yield point and then you have a normal curve. So why this yielding happens while there is a yield point phenomenon occurring in the material and which of these materials is responsible? So first, you try to answer this, then we can discuss.
Steel.
Right. The steel is why? Can you tell why?
No, 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 never have the exact reason.
Okay, right. So if you see steel, what is the difference between steel and all other elements in this question? What is so common in steel that copper, aluminum, and silver does not have?
Steel is a alloy of iron.
Right?
Others are non ferrous metals.
Yes, they are non-ferrous metals and they do not have some extra additions or impurities or say for example atom additional atom in them. So what happens in steel that you have say for example you have interstitial atoms like for example carbon, or sometimes if you are also imposing hardening it, so you have nitrogen, some kind of atoms that are added intentionally to steel. So by addition of these atoms, what happens that you have the interstitial spaces that are being occupied by these atoms. So these atoms here are acting as a pinning agent, so they hamper the movement of your dislocations. So that is why you have a higher yield, first higher yield point, because you have to overcome these points, these interstitial atoms, in order to cross over them for a dislocation. For example, if this is atom of carbon, the dislocation has to bypass this atom of say for example carbon. So for that you have a certain you have to impose some extra additional force for this dislocation to move across and to move further. For that you have this point of yield which is this, right? But once it has crossed and it does not have any other impurity on its way, so your yield point will drastically decrease and then you have a normal stress strain curve. So this yield point phenomenon only occurs because there are some additional atoms present inside the material that will hamper the dislocation moment, and as a result your yield point phenomenon, you will have two yield points, one upper and lower yield point. Okay. So next question is that the value of your critical resolved shear stress dash with increasing impurity content in a metal crystal. So what happens if you have a say for example critical resolved shear stress and you have an impurity inside the material? So will it increase your critical resolved shear stress, decrease, or what happens?
Increase.
Critical resolved shear stress is nothing but it is a amount of stress that you have to apply on a material for a slip to occur, right? If you have a more impurities inside the material, what will happen to the force that you are applying on a material to for a deformation or for a slip to occur?
We have to apply higher stresses because hindrance
Hmm. Right.
introduced
So
by these impurities.
so your value of the critical resolved shear stress will increase with increasing the impurity content, because more impurities, more hindrances, and as a result uh, you have to apply a greater shear stress for a deformation or for a slip to occur in a material. Okay. So then we have another question that says that the extent of deformation due to mechanical twinning is dash, then due to slip. So you have to say that if you have a material, you have mechanical twinning occurring in a material and a slip occurring in a material. So which of the two will have a more deformation effect in a material, whether it is twinning or slip? Right, because twinning does not have a major role to play in your deformation as much as slip. Slip is again the movement of your complete plane across a slip plane, right? While as twinning is across your certain arrangement of the atoms that occur along mirror plane reflections they are inside the material. So the deformations are not that drastic in case of twinning, but they are very drastic in case of a slip, right? So I think slip is much more for extent of deformation. This is also like for example in your HCP structure, like is magnesium. They are more like soft material as compared to say for example aluminum. Magnesium is a HCP structure. Aluminum is say it is FCC structure. So they are having two different structures. They because of their difference in structure, their mechanical deformations will be different. There will be more chances of slip in a FCC structure, while there is more chances of twinning in your HCP structure. So that is why it is much softer, while as in your because more slip can occur, so more deformation can be possible. So that will also influence your properties of the material. So you should understand the crystal structure, their slip systems, and their ultimately the effect of those slip systems and deformations on your mechanical and other properties. So I think that is now we have one more question. So it says that this is a numerical question, right? So we can say that a tensile test on a cylindrical specimen made of a material with an initial gauge length of 50 mm and an initial diameter of 10 mm. Okay, so this is a question that is based on your engineering stress and true stress. Okay, so you have a material, initial material. You have some material like this, so cylindrical specimen. So you have a length of the material given, and you are given the initial diameter. So this is 10 mm. So you know this is your initial diameter of a material. 10 mm, and then it says the material undergoes uniform deformation until fracture. During the test, the load and the corresponding elongation are recorded. From these data points we can calculate both engineering and true stress at each point. So you have to calculate the I think you have to calculate the yes, engineering stress and true stress. So first I will try to get this question here.